Hello, good afternoon. So everybody can hear me? Can you guys hear?
Yes.
Okay, thank you. Excellent. So happy Good Friday when we are going to cover some good stuff today. Let me remind you, today is April 10th. It's our week 12 lecture B. So let me share the screen. Okay. So far, we have done difference equation, Z transforms, inverse Z transforms, properties of Z transforms, IVT, FAT, and initial conditions, and so on and so forth. Okay. So, and we talked about House transfer function and talked about the polynomial product. So all these things based on the assumption that you have a continuous signal, then you need to sample it. So like here, if you sample this one, and so this is a continuous time signal. This is a discrete time sequence. So you can see if I sample very slowly, you don't see this is a sinusoid. Okay. So how fast we should sample? So today is week 12b, is Good Friday. Good Friday. What information do we lose? Okay, do we lose in sampling? So you sampling, you lose something in between, right? So, but from frequency domain, so frequency domain, we want to have a closer look to see what we have lost after sampling. Okay, and based on that, we are going to see how fast we should sample. Okay, so that's called sampling theorem. Then we are going to really take a look of the S and Z relationship. S and Z relationship. We are going to have a very good idea about aliasing. And I have developed an example that I show you how we can draw what is the aliasing frequency. Okay. All in all, we are ready to move forward. So suppose you are giving a discrete sequence like this. The question is, what is the original continuous function? Okay, you thought this is a constant. You are right. You are not wrong. Okay. But this is only one possibility. There are other possibilities. Okay, like that. Okay, it could be an oscillating sequence like this. So so behind this sampled sequence, so the continuous signal could be otherwise. Okay, could be otherwise. How we can uniquely tell? Okay, uniquely tell. This is the continuous function. That needs extra work. So you can simply say that if you can sample a little bit more points, then you would be able to tell this is this signal, okay? Okay, so otherwise you thought this is a constant. So in other words, if the original continuous time signal is like this, and you only sample slower than necessary, then you end up with something discrete sequence that you cannot go back. I don't like the go back, but it's not wrong. It still can say go back, but from signal processing point of view, we have another word. Do you know what's that? It's called reconstruction. Reconstruction. So in other words, from these black dots, you cannot reconstruct this original signal if it is like that, because you sampled too slow. Okay, too slow. You cannot reconstruct. So there must be something behind everything here, like really, how do I know I'm sampling slower than needed? How do I know I'm sampling it just fast enough? So that kind of question. So to do that, we have to learn some math. So you have a continuous time, you have discrete time. You only have these dots, okay? You only have these dots, nothing in between, okay? Remember, nothing in between. Remember, I think a long time ago, I gave you an example saying that I have a function in here, f of t. I only want to pull out the specific, like, let's say, t0 at here, okay? How you can have a signal going through some sort of black box, then you end up with ft0. You only have one dot left, one dot left. So in other words, you're trying to pick up the specific point in here. How we do that? So how we do that? I told you that it's possible because if I say my output here is ft, and we do delta t minus capital T 0 and dt, oh, I'm sorry. This one is minus infinity to positive infinity. That one will give you ft0, right? So this guy is called impulse function. It is not zero when, it is zero when t minus t0 is not zero, okay? So delta t is 0 when t is not 0, okay? But can I say delta t is what? When t is 0? When t is, wait. When t is 0. I don't know. I don't know how to answer this question. Is actually they should not define this way. It's not defined in that way. It's only defined in such a way such that I don't know what is a delta 0. I don't know what is my delta 0, okay? I know delta 0 is not 0, okay? Yeah, but what's really is, we should say, is 1, okay? It's 1, okay? It's 1. But remember, for all t not 0, it is 0, okay? Of course, I told you that you can imagine that you have a rectangular thing in here. So you have a delta, and here you put 1 over delta. So then shaded area, what's is the area is 1, okay? So then you send this delta to 0. you are going to see this rectangular will have 0, okay, side is 0, and height is infinity. So then somehow like, so one side is 0, another side is infinity. You don't know, this is not defined how to do 0 times infinity. Can you say 0 times infinity is 0? I don't think so. Okay. Can you say, actually, you should maintain the error is 1. So that's the prototype of impulse function. This is very interesting. Okay. So again, I'm writing something like that. So like if you have a delta minus t0 f of t, then you do d dt and minus infinity and infinity. That will be picking this point out. It's ft0. Okay. However, don't get confused. Some students say that, hey, delta t ft is what? I don't know. I cannot say anything about it. Okay. I only know that is delta t, delta 0 f0. Okay. I don't know what's that. I don't know because I don't know what is the delta 0. Okay. I don't know. So you cannot say anything further than that. So this is called a sticky case. It's a sticky case. Sticky case. So I'm trying to say, review that though. So basically, if I need a point in KT, any point in KT, then I need delta T minus KT. Make sense? Okay. So then I add everything together. It's like integration. Okay. Here in discrete sense. Okay. So this is called the pulse train. Okay. Impulse train with a T interval. T is my sampling period. Okay. Sampling period. So this is K times T, how many sampling points. So in other words, I'm using a star, F star here, to be said is a sampled signal. So this is called, this star here is called sampled signal. So sampled signal. So sampled signal can be written as original continuous time signal and multiplied by the pulse train. So that's it. Okay. Okay. So this is called sampling process in mathematics. Yeah. Let's recall. If we do integration of this delta, you get a step. Okay. So this is an impulse. So you do integration, you have this one. Okay. Unit step. But if you have this one minus this one, so I know that this FKT only true when this one. So this is called shifting. Okay, it's called shifting. Okay, shifting. And remember, Laplace transform of the delta will give you 1 here. Okay, give you a 1 here. So that's why we simply say that you have a transfer function g of s. So you have a so you have input is 1. Y of s is y of s is g of s times 1. So this is input, right? Input. So therefore, that's why we call inverse Laplace transform of g of s is called g of t. It's called impulse response. Okay, impulse response. So this is actually a impulse response. If you do inverse Laplace transform of the transfer function itself. It's like you put the impulse in here, you get a response. Okay. So let's try to check what is the Laplace transform of this f star is called sampled. So please focus on that. You'll feel you achieve something on this slide. Okay. Please, please, please. You'll achieve a lot if you focus on this slide. A lot of students may feel scared about it, but this step is nothing but this is the original signal. It's called sampled signal. This is just by definition, right? This is definition. This is Laplace transform definition. Now I'm insert, because I developed the previous one, I'm insert this equation into here. So I'm simply inserting here. So still, this is nothing but this, right? So we have, again, this is copying that term, okay? So interestingly, what we're trying to do here is we're trying to, because when we multiply this one and sigma that, if we swap this summation with this summation, of course there are some conditions you need to satisfy. You put this one on front and then put it back. So basically you are integration. Remember, we're doing minus infinity plus infinity, then f tau delta tau minus kt, and okay. So in that sense, and e minus s tau d tau, okay, d tau. What we are going to get? What are you going to get? So this one, you know that is 0 when t is not kt. So sorry, this is not t, this is tau, okay? So you should put the tau here as a kt, okay? And you also put k, you should put k times t to replace tau. Also, you should do this. So you have, that's why you have skt, right? Skt. So then you also have fkt. So you have fkt and e to the power of skt, because you are integrating with this magic delta. Okay. So again, we used the formula, but now we have two terms. One is f tau, e minus s tau. So just have this one left. But remember, I have this one. So this is an important, so this is a Laplace transform of f star. So I say this is f star, and f of s, we denote this one as f star s. So this is a f star and capital F star as a Laplace transformation pair, okay? Laplace transformation pair. Okay, can you guys hear me? Have some internet issue, do I?
I can hear you fine.
Oh, okay, because my other phone is saying, oh, I got lost to my, okay, so it's false alarm. So, okay, so if we write this guy into this term, okay, so say minus k in here and st in here. Remember, if somehow I can say z is st, then I'm going to write, by definition, this is a discrete sequence. So then it is exactly the z transfer function of that sequence, sampled signal. So I think I gave you a clear explanation at this point. If you are not lost, congratulations. Okay. So from this derivation, we didn't assume anything. So we recognize that this is by definition of a Z transformation, okay? Z transformation. So you have Fk, okay, and Fz. So this is Laplace transformation of the sampled signal. And so we recognize that Z and S are linked exactly relationship. It's called exact relationship. So, and T is the sampling period, okay? Sampling period. Okay, I'm going to move on. I don't think this is hard to swallow because everything's from definition, and the only trick we did is swap these two summation here, okay? Summation. So I have a pulse train. So this is my pulse train, okay? I have a pulse train. I can, for delta, what is delta's Fourier transformation series? According to the definition, it is like this, okay? 2 pi n divided by t, and t, j omega t. So t is here, t is here, okay? Fourier series means you have any signal, including this delta t here, can be expanded as summation of sine and cosines, sine and cosines. Okay. So that is in any textbook about Fourier transformation. About Fourier transformation table, you can check out. This is true. Okay, this is true. So now we are trying to again do this Laplace transformation of the sampled signal. Again, this is the definition, okay, definition. And we put in ft in here, okay, ft in here. And so this is Laplace transform, we didn't change. What we did change is this term, okay, to expand the delta t minus k into this term, okay, into this term. All right. By putting in here, we do the trick again. So we have this sigma put in front, and put this sigma in swap the sequence. So again, I have f of t, okay, and again I have s of t. But what is this term? What is this term? This term we only have this one left over, okay, left over here, because I remove this sigma in the front, okay. By swapping that, so this is this one left, I copy in here, okay. Then I'll inspect what's this. So ft is here, but this one actually can be added together, will become a minus s here. Then this is a positive, so you should negative in here. Then j 2 pi n divided by t, and all the bracket, then you have t in here. Okay, t in here. Okay. Remember, we write ft est dt minus infinity to positive infinity. This is what? This is fs. Okay, ffs, Laplace transformation pair. But now we are actually shifting the s, okay, shifting the s in here. Okay, shifting the s in here. So basically that is linked to here, okay, linked to here. Okay, so let me ask you about something like, so still remember e to the power of at ft So let's say a greater than 0, then f t and capital Fs are Laplace transformation pair. Now I'm asking you, what is this one? This is S minus A. Okay, S minus A. Okay, that's why you can compare. You can treat this guy as A. Okay, this whole thing. So this is the A. Okay, this is the A. So that's very interesting to look at the system, and so it becomes the infinitely many terms in here. So don't worry if you feel a little bit fuzzy here. Don't worry, it's because you feel like your Fourier series is not very good. So so I'm trying to tell you that we inspect the Laplace transformation here, and we end up with this one. If we apply the expansion of Fourier series, the expansion of the delta signal, we end up with this one, okay, and this one, okay. Let me do this. So let me do this. So I said ft and fs is a Laplace transformation pair. We also did f star t and f star s as a Laplace transformation pair. So my question is, how f of s linked to f star? So basically, this term is f star s. Okay, this term is f star s. Okay. So how we can use the continuous times for Laplace transformation capital FF to represent this one. It is linked to like this. It's not one term. It's infinitely many terms with the shift. And the n will change. Okay, n will change. Okay. So you can write 2 pi divided by t. You can write this is like omega s, the sampling frequency, angular frequency. So this one will be like j omega times n. Okay, the n is changing from this. So there are some huge consequences in here. I'm turning this. So this picture shows you that in general, the continuous times original signal, before you sample it, we usually assume it is narrow band or band limited signal, meaning this is a magnitude of the Fourier transformation. This is a frequency. So this actually is called a spectrum plot of f of t. Okay, f of t. So if you become a zero, this becomes 0 when the frequency is high. Okay, and at a certain point, the b, beyond the b, all the signal will be 0, meaning the frequency has a content in the signal original f has an upper bound. Okay, so this is called band limited signal, which is true. Let me give you an example. Okay, give you an example. Say for example, you have sinusoid. Okay, if you have sinusoid omega, okay, so say this is your omega. Okay, omega 0. What is the spectrum of that? It is simply a vertical line. Okay, you only have one point in here. Okay, a vertical line, one point in here. Okay, that's your omega, and this is your magnitude. Okay, magnitude. So, but in general, we can assume that my original signal is band limited. But the question is why we have a negative here, negative B. Yeah, that is exactly from a Fourier series point of view, and we can expand the frequency into the negative ones. So mathematically speaking, okay. So what does that mean? What does this mean? What does this mean? This visualization of this one is, okay, you are going to have original, this is your original F of j omega, okay? So this thing is your original continuous f j omega, okay? After sampling, you have f star j omega. You are going to have, this is n is 0, n is 1, n is 2, n is 3. So basically you are shifting this n and you are making a copy of it, okay? A copy of it. So omega s is a sampling is 2 pi divided by t is the omega s. So basically you have here, you have omega s in here, 2 omega s in here, okay? And 3 omega s in here, dot, 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 okay? It duplicates infinitely, okay? In other words, say for example, okay? You have a sinusoid, okay? And you sample it. Then after the sampling, you have a discrete dots. But if you study the spectrum, this is its spectrum, okay? F star spectrum. You are going to see, so this is called a single tone. Remember, if you play an instrument, you have a metronome, right? So you have some tone, right? You can tune this instrument. So that is only one sinusoid of one frequency, okay? One frequency. Okay. But after you sample it, you have dots. How many frequencies in there? It's no longer a single tone. It becomes infinitely many frequencies, okay? So for example, you have originally you have a omega 0 in here. Omega 0 is your single tone, your frequencies here. Your metronome will give you a 1 here. Then after you sample this sinusoid, single tone, so you are going to have make a copy of it. So you have this one, you have this one, you have this one. So you have 1, 2, 3, 4, da da da, to infinitely many sinusoids with different frequencies add together. Okay, add together. So let's pause and think. Whenever people ask you, oh, this signal is sampled, then after sampling, how many frequency contents in the sampled signal? You don't need to wait in any minute. Just say infinitely many, okay? Because they are going to duplicate. So this is explained using this equation, okay? This is the equation, okay? So mathematics is important. So this equation visualized is this way. Again, we are talking about frequency domain interpretations of a signal before and after sampling. So before the sampling, my j omega is only this gray, okay? After sampling, the spectrum is including this gray, as well as infinitely many of the copies of it and shifted by from 0 and centered at the sampling frequency, okay, to 1 omega s, 2 omega, 3 omegas, all the way goes to infinity. All right. So trust the math, believe in the theory. You have single tone continuous sinusoid after sampling, and you will have infinitely many components, frequency components in there. Okay. That's the answer. But unfortunately, remember, we got something called a B in here, right? So we are going to have a band limited signal, and everything beyond the frequency B, it will be 0, okay? Everything beyond the B here is 0 in continuous time domain, okay? However, after you sample it, it is sampled not fast enough. Therefore, there is an overlapping here, okay? You sampled not fast enough, then the scenario is like this, okay? So then this region is called ambiguity, okay? The sampling frequency is less than the twice of the maximum frequency 2b, okay? So this is sampling frequency omega s. It is not 2 times, so this is only 1 point something. Of course, it could be even worse. Okay, it's less than 2b. Okay, omega s less than 2b is you have overlapping. Whenever you have overlapping, that means you have an area of ambiguity. You have overlapping. That means you cannot go back anymore. Why? Okay, I'm going to show you in the next slide. So I already said you have sinusoid, single term. Sorry, single term. Then you sample this one. Okay, so this one has infinitely many frequencies contained in there. Okay, so in the frequency domain, so the continuous is, this is omega 0. So this is omega 0, okay? Only one omega 0. But if you do this, this is a time domain, okay? I'm drawing the frequency domain. In frequency domain, what are you going to have? Omega 0. You still have omega 0. But you will have, this is omega s times 0. This is like, say, omega 0, omega s in here. So then this is the center, so you will have another. So this is the another one. You can continue the whole process. Okay, whole process. So these are the components. Omega 0. This is the omega 3, omega s plus omega 0. Okay. So you need to shift. Okay, shift. This shifting distance is omega 0. Make sense? Sorry, I'm sorry. Apologize. This is not omega 0. This is omega s. Okay. So basically you hold up and shift omega s. Then you shift omega s again, so you can keep going. Okay. So you have 100 hertz. This is 100 hertz, and your omega s is exactly equals to b, right? Okay, it's 2, because now the b is 100 hertz. Okay, so you sample 2b, then you are going to have a 100 hertz. You sample that 200, so this is your 1 omega sampling. Okay, so then you move from here to here 100, so you will be 300. You get another one. So, but let's draw another one. So what are you going to do? So you draw what is 2 omega s is 400. Okay. Then from 2 omega s, you need to move 100 with the b. Okay, 100. So then you have 500. So the next pulse is 500. So this is 500. Okay, so you can keep going, but there's a so this is 100. You basically plus omega s, you get 300 plus 2 omega s, you have 500. Then you can keep going. So it's a duplicate of this original spectrum. Okay, duplicate. So life is so far easy. Okay, so if you sample fast enough. Okay, what if I don't sample fast enough? Okay, that is called aliasing. So we still do 100 hertz, but I sampled at 150 hertz. Okay, so I'm going to say this is my 1 omega s. Okay, where is my 2 omega s? So this is 200, 250, and 300. So 300 is here. Okay, so this is my 2 omega s. Okay, so this point is my 0 omega s. Okay, this is my original singleton in here. Okay, original singleton, 100 hertz original signal. I'm going to check what happened. Okay, what happened by sampling not fast enough. So this is less than 2b. Okay, less than 2b. So I'm going to have overlapping. What does that mean? So that means when I come over here, okay, over here. So I move all this, I move everything here from 0 omega s centered here. What is my next component? Is measure 100 hertz from here, right? So 100 hertz from here is 250. So this is my next. So this is 250. This is 100. And the distance between this one is my omega sampling period, okay? Sampling frequency. Okay, makes sense? On the other hand, remember here, I'm duplicating the whole shaded area symmetric to -1. So I actually, when I have omega 0, I should have a minus omega 0. Okay, minus omega 0 in here. Okay, minus omega 0 here. So what I'm saying is you lift everything you place in here, so you only have one here and another one here. You have another one here. Okay, so you have two. Actually, you have two lines. It's just neither. You have two lines. You move together. Okay, move together. So based on that principle, so my original signal. Let me see this example, 200 hertz example. In fact, the original signal, you have this one, then you should have a minus 100 in here, okay? So then you have something here. So this is your negative omega, okay, 100 hertz in here. So basically you are going to make a copy of that. So the copy is you put over here. So you go here 100, go here 300. No, 200 is your 1 omega s. Go here you have 100. Go here you also have 100. So this actually has two just overlapped. Okay, that's a good thing. Okay, so we didn't do anything wrong. Okay, didn't do anything wrong. Keep moving like this. But for this case, it's different. Okay, it's different. So let me do this one for you, and please pay special attention. Okay. So what I'm going to do here is the original is 100. So this is minus 50, this is minus 100. So this is the original bar in here, okay? Original bar in here, okay? So I centered at 0 omega s, okay? Omega s. So then I move, remember, I move this green one and this one, lift them and move it centered at 100. So let me put this one as like this is 1. This is a 0. Okay, this is 0 prime. Okay, prime means I'm centered at the 0. Prime is left, right is no prime. Okay, so 0, that's 0 prime. So I'm going to lift this 0 prime line and 0 line, and originally they centered at 0. Now I let it center at 1, and I use another color to place it to, let's say, blue. Okay, the blue. So I lift from 0 to 1. Then this guy will become what? You shift is here. So 0 becomes 1. 0 prime will becomes 1 prime. 1 prime. Okay, so you shift that. That explains why I have a 50 hertz in here. Okay. Okay. And you keep doing this. You can keep doing this. You can draw 2 prime and 2. Okay. 3 prime and 3. So you know all the components. Then you just rank them. Okay. All right. So you have 2. You have left and right. You move them together. So the reason I do this one is to show you, because a lot of people don't understand where this 50 comes from. Okay. Yes, it has a 50 hertz. 50 hertz. This one is smaller than original your system here, degree. So if you do a low pass filter, you can filter out all other high frequencies, but you cannot filter this one because otherwise you kill yourself, right? You cannot do low pass filter or high stop filter to remove this guy. This guy will stay. Okay. This guy is called aliased signal. It will stay and it will distort your signal. Okay. In other words, because of this guy, because of this 1 prime, because of this 1 prime, because of this guy, then it is already mixed into your 100 hertz. So then you try to recover this signal after filtering. I mean, it's low pass filtering, a low pass filtering. It's not be possible. You will never get 100 hertz back because it's corrupted with a 50 hertz. So it's not going to come back. So the consequence of not sampling fast enough is you are going to get extra aliased signal that is smaller than your frequency B, okay, within your B. So that shows smaller than your B. You have something here, okay? You have something here, aliased, okay? You cannot come back. Got distorted, okay? This is will distort you, okay? So I hope at this point you have a firm understanding about the consequence of not sampling fast enough, okay? Not mathematically, but also not only mathematically, but also graphically. So now we understand we need something called Nyquist frequency. Sometimes people do a Shannon Nyquist. okay, or Shannon's sampling theorem. That means you have to sample fast, faster than 2b, okay, this one, not slower than 2b. Then you can still reconstruct. Look at this word, I like it. You can reconstruct the original system from the samples by doing what? You get rid of all this infinite frequency duplicates. You have infinite duplicates. Just put a low pass filter, just low pass filter. You keep this and throw away others, okay? Then you can say we recovered. So that is exactly what we said. We attenuate all those are not, I don't want this one. I just add a pass filter like this, okay? I will be able to get this job done, okay? Okay. So this thing is called anti-aliasing filters frequency characteristics. Okay, frequency characteristics. So you have you can stop in here, so it will be fine. Okay, you can keep it. So it's called anti-aliasing filter. So in all the data acquisition systems, you have inherently built this anti-aliasing filter. So that's why you are fine. So you don't see it. So, but it's there. You should know that. Anything you sampled, it will have duplicated spectrums like this. But you can low pass filter it if you sample fast enough. Okay. So right now, I hope this is a sampling theorem and how fast we answer the question, how fast we should sample. Then you need to have a basic idea of how big is your B, meaning what's the signal's frequency, okay? What's the signal frequency? The answer is, you have an estimation of it, okay? Then you do 2 times of this one. So usually you sample, actually to be safe, is 2 probably not enough, maybe 4 is even more. The higher the better, okay? But higher the sampling frequency, the higher the cost of your hardware. You have to do faster. So and also your data processing has to be faster. And in reality, we need to be careful about the cost. Now, in the next 20 minutes, so we are going to finish up about relationship between S and Z, okay? Sampling unit. So this is, we have a name of this one, did I tell you? People don't, Heaviside function. People don't use Heaviside a lot, but I told you I respect him, Heaviside function. And then after sample, you got all these impulses, okay? Discrete points, in fact, discrete points. And this bar, well, actually, we should not draw it. It's not there. Just discrete points, okay? Discrete points. So basically, you can write something like this. So let's do a Laplace transform of my sampled. This one says sampled. Is this guy? Okay, this guy sampled. So the sampled one is Laplace transformation. Then end up with nothing but this one. And this one compare, it is exactly like this, okay? So from this connection, and this is from definition of Z transform. So this is always 1, okay? Sequence. So compare this one to this one, we can say Z is EST. Remember, we already derived this one. Do you still remember? we use a Laplace transform of a step. We have seen this. However, we actually have seen this one. This is the second time I have seen this. We have already seen this one here on this page, 75, page 75. Okay. So now we arrive at the same conclusion. Okay, same conclusion. Okay, so this allows us to interpret the z variable in frequency domain. Say, for example, when S is j omega, okay, I have gj omega, okay, so I can do frequency and analysis based on that. But what if I have a gz? Don't worry, I just do z is ej omega t, ts. So you put this one in here, you can still compute the frequency response. So you still have a magnitude and phase, okay? Magnitude and phase. You can do body plot as well. Okay, so this is beautiful. I'm so glad that we cleanly arrived this step. Okay. So, but in reality, you can see that this is not algebraic, not polynomial. It's a transcendental function. It's exponential or logarithm. It's difficult. So this is difficult. So then we are going to check, okay, G of S, can we tell it's a stability? So you have a polynomial, you can use a Rose-Horowitz table. You can use body plot, gain phase margin. So you can check stability, and also we can check the constant frequency, constant damping ratio, that kind of stuff we have learned if we stay in a second order system. So if you check omega n square plus 2 epsilon cos e omega n and s square. So this is a typical second order system. Usually we use this one as a role model so that we want the system to behave like this. Okay, then design a controller to achieve that. But in frequency domain, and I'm going to show you that because S is a complex number, so Z is also a complex number. So in the complex plane, okay, complex plane, left half plane is where your poles should locate such that the system is stable. But let's try to go from A, B, C, D, and we're going to check. So this is my A. When everything is 0, remember, when S is 0, 0, 0, okay? Okay, when S is 0, then Z is 1, okay? When S is minus infinity, okay, and then it will be 0, okay? C and D goes to infinity, it will be 0, okay? It will be infinity, okay? And B is imaginary, goes to infinity, 0 plus J infinity, okay? So you put it there, okay? So you are going to end up in here, okay? And similarly, you can do, so this is S domain, S plane, this is Z plane, okay, Z plane. So both are complex numbers. So by doing that, you are going to see, well, I'm closing this shaded area, it can map inside here. So in other words, inside here, this is called unit circle, okay. So GZ, all the zeros of Z, all the poles of the Z transfer function has to lie within the unit circle to be stable. remember we have a lot of terms like a to the power of k. So a less than 1, then it's converging to 0, right? If a greater than 1 is here, okay, so then it will blow up to infinity, okay? So it's imaginable, The stability region of this corresponding to the stability region in here per this conversation, per the conversion formula. So so we are going to continue. Let's pause a little bit. Let me put in my power supply. Got 10 minutes left. It's not enough for my power. I'm going to put in my, let me see. I'm going to stop my video. I'm going to move to my power supply, and we're going to continue. So let me go to the next page. So can you take a look? So what is a constant damping? So I have to mute myself for just okay, I'm back and with my power supply. I proved today that my battery is not fresh enough to sustain 75 minutes for my whole class. So, but very surprisingly, when I bought this computer, they said that the battery time is 9 hours, okay? So I bought it. So very funny, 9 hours. Now they cannot sustain me 75 minutes for my lecture. So I'm not happy about it. But there's one possibility that because I'm recording, I'm using video, I'm using internet, I'm using audio, everything. So that's why. Okay, let's come back to talk about constant damping, okay? Constant damping, basically, okay? Constant damping basically is this line, okay? So you have a real part is a constant. It's called constant damping. Then if you have everything in here, you have a pair of poles in here, you always have e to the power of minus sigma t to decay for sure, okay? For sure, that decay. So in other words, your system in the time domain, you will decay like this, okay? But sometimes you say, oh, actually, I have sinusoid decay, but the envelope will decay like that, okay? It will be, like this case, okay? This case is sinusoid, decaying sinusoid. But based on what we know, S and Z relationship, put it in there. So this black line will correspond to this smaller circle, okay? So I hope you know this. So this is very interesting. So if you have a constant omega, meaning you have a constant omega, but real parts is different. So this is a constant omega. So I put this one as a constant, and I'm putting C here, okay, here, okay. That means what? You have a EJ omega TS, okay, EJ omega TS. So S is J omega, put it here. So Z is, yeah, okay. So constant J omega is to a point here, okay, okay. With phase omega TS. TS is known, okay, TS is known, okay, is known. So it's that point. And all you can talk about, okay, we have seen this one, and the second order estimate model. Cosy is a damping ratio. What if my damping ratio is constant? Okay, based on our study, we know that is this line. Okay, is this constant Cosy line? In this is estimate. Okay, estimate, and we replace this one into us. Do some math, and in this locus of the constant damping ratio, basically you have this line, okay, this line. So remember that is this line, okay, constant damping ratio, okay. So this line will become something like this. So how do you do this correspondence of mapping? So basically you can deduce Z domain and the stability. Depending on the position of the Z transfer function's pole. And using that pole, you can tell the damping ratio or the damping, okay? And this is good for root locus design, which we ignored, okay? Okay. We only focus body plot. So this is a computation of closed loop pole location. So usually you want the system to be stable, or you have a oscillatory response, something like that. Then your pole probably is located like this, complex conjugate, okay? Complex conjugate is within, this is called a unit circle, okay? Unit circle. Okay, so we return back to this one to remember in this A is, so S is minus A is your pole. P is minus A is your pole. Okay, minus A pole. A positive. So the A, if the A is bigger, that means you have a faster decay. So this is A. If A goes this way, you mean your decay much faster. If an A is negative, then this side then is unbounded, meaning unstable. If A is 0, okay, A is 0, then you have an integration. So this is 0, then 1 of S is integration, right? So by comparing the sampled data, we have learned this before. T is my sampling period. So large A, you have smaller r, a fast decay. So again, so this is a unit circle. Then you have a smaller circle as A goes big. Same thing. Okay. So when A is 0, then R is 1. That means there's integration. So 1 over S becomes 1 of S on this side becomes, okay. So in other words, I'm doing I inverse both sides, okay? Both sides. This is the inversion of 1 of s, okay? But then this is z minus 1 divided by z, right? No. I need to inverse this one. So it's a z minus 1 divided by z. So in other words, it is 1 minus z minus 1 is my s. Okay. So from this exponential study, we have find out s and z are connected with this equation. Surprised. But through all the analysis, we said that s is e to the power of z times ts. Oh no! It's different. Sorry, so z is minus. Oh, okay, that makes sense. Okay. But remember, if ts is small, okay, then I can do. We know that ex is 1 plus x cubed, So basically, I can simply say these are the high order term is x is very small. So in other words, this is approximated is 1 plus st, right? Yes. So in other words, if I do so it will give you a z minus 1 divided by ts, okay? It's approximately like s. So I'm not sure I'm confusing you here, but that's fine, that's fine. You say, oh, I lost z in here, so compare this one to here, lost the z in here. That doesn't matter, you just shift 1 point. 1 point. So z is a shifting, right? Z is a shifting. So, but you can see there is some reasoning. They are all connected here from the signal analysis point of view. Here we can do a complex conjugate. Okay, so it's a complex conjugate. So then you have a sinusoid. So then second order complex conjugate, you end up with this. Okay, while the theta is this, the r is this. Okay. But remember, if b is there, okay, so no, you cannot. So you end up with a second order z transfer function like that. At this point, we are going to stop after I said this, okay? We'll have more materials to cover next week. So regarding controller design in the Z domain. So Z transform relies on the ideal sampling, okay? Ideal sampling. So that is what we have in here, okay? Amplitude of the pulses. But in reality, you cannot give a signal simply a point. I think there's a word called a pinch, okay? So you cannot pinch the system, right? So it's practically not realizable. So we need a hold device called holder, okay, holder. So basically, if I have dots, like so I hope I can hold this guy. So then I can hold this guy, hold this guy, hold this guy. So that becomes my holding. So this looks like a continuous signal. Okay, looks like continuous signal. Okay, so this is called holder. So holder will make the discrete dots into a constant holding staircase type of signal like this. Then you apply this one to the real system, is no longer pinch. So it's called piecewise stepping signal. Okay. So our time is up. We're going to continue to talk about next time. This is called zeroth. Okay, zeroth. Then make this system more practical and realizable. And the current digital system are all in that way. So I'm going to continue to discuss what is the transfer function of this one. Okay, what is the, so this is a device, that means you have in and out. So what is transfer function here, zeroth? That's a very interesting question, okay? So we are going to answer this question next Wednesday. All right, so do you have any questions you want to ask? Let me check my, I haven't checked my chat box. Looks like there isn't any, yeah, there isn't anything. There, so if you don't have questions in the next 3 seconds, I'm going to end today's lecture, and it will be recorded. I'm going to upload to the YouTube and make it for public. So if some of you didn't attend today's lecture, I have 19 students in here. I got 18, less than 50%. So looks like everybody is busy. And I understand it's Friday. And I understand, you understand that it will be on the YouTube. You can watch it later, okay? But you do need to put in the efforts, okay? And this part is critical because I told you, you are going to face the digital control no matter what, okay? With that, I'm going to end today's lecture, and good luck. Have a good Friday, and take care, stay safe, okay? Bye-bye.